sklearnsvmSVC. Description: the SVC Support Vector Classifier class in scikit-learn is a powerful tool for implementing support vector machine SVM algorithms for classification tasks. SVM is a supervised learning model that aims to find the optimal hyperplane that separates different classes in a multi-dimensional feature space. Inputs: X. This is a 2D array representing the input data. Each row corresponds to a data point, and each column represents a feature. Y. This is a 1D array containing the labels or target values for each data point in X. The labels should correspond to the classes you want to classify. Outputs: self returns the trained SVC object itself, which can then be used for making predictions on new data. Decision function X returns the distance of each data point in X from the decision boundary. Steps: data preparation. The input data X and labels Y are prepared for training. Kernel selection. You choose a kernel function that defines the similarity between data points. Popular choices include linear kernel, simplest kernel, suitable for linearly separable data. Polynomial kernel allows for nonlinear boundaries. Controlled by degree parameter. Radial basis function RBF kernel widely used. Creates nonlinear boundaries with a Gaussian-like influence. Hyperparameter optimization. Parameters like C regularization strength, gamma kernel coefficient, and others are tuned to achieve optimal performance. Model training. The SVC algorithm finds the optimal hyperplane by maximizing the margin between the classes. Prediction. The trained model can be used to predict the class labels for new data points. Metrics: accuracy, the proportion of correctly classified instances. Precision, the ratio of true positive predictions to the total number of positive predictions. Recall, the ratio of true positive predictions to the total number of actual positive instances. F1 score, a harmonic mean of precision and recall. Balancing both metrics. AUC, area under the curve, measures the overall performance of the model, particularly when dealing with imbalanced datasets. Visualization plots. Decision boundary plot visualizes the separating hyperplane in 2D or 3D space, showing the decision regions for different classes. Scatter plot with support vectors displays the input data points with support vectors highlighted, indicating the data points that contribute most to the model. Fine-tune parameters. C regularization parameter. Higher values emphasize correct classification of training data, potentially leading to overfitting. Lower values allow for some misclassifications, which can help with generalization. Kernel, the kernel function to use. Different kernels, linear, polynomial, RBF, are suitable for different types of data. Gamma kernel coefficient for RBF and polynomial kernels controls the influence of individual data points. Higher values give more influence to nearby points, while lower values consider a wider range of points. Degree of the polynomial kernel. Higher degrees create more complex decision boundaries. Uncertainty methods. Confidence scores. The decision function output provides an indication of the model's confidence in its predictions. Higher values indicate greater confidence. Challenges and fixes. Challenge 1: overfitting, when the model performs very well on the training data but poorly on unseen data. Sample use case that resulted in challenge 1: a high value of the C parameter, combined with a complex kernel, might lead to overfitting. Fixes to challenge 1: reduce the value of C to allow for some misclassifications. Simplify the kernel or choose a more suitable one, e.g., a linear kernel if the data is linearly separable. Use techniques like cross-validation to tune hyperparameters and evaluate model performance on unseen data. Challenge 2. Computational complexity training SVC can be computationally expensive, especially with large datasets and complex kernels. Sample use case that resulted in Challenge 2: a dataset with millions of data points and an RBF kernel might lead to long training times. Fixes to Challenge 2. Consider using a simpler kernel like the linear kernel if appropriate. Use techniques like dimensionality reduction (PCA) to reduce the number of features. Utilize parallel processing or GPUs to accelerate the training process. Challenge 3. Data scaling. Scaling the features to a common range, e.g. 0 to 1, can improve the performance of SVM. Sample use case that resulted in Challenge 3: features with widely varying scales can influence the model's performance. Fixes to Challenge 3. Use standardization or min-max scaling to bring all features to a similar range. Consider using specialized techniques like robust scaler if the data has outliers. Challenge 4. Choosing the right kernel. Selecting the appropriate kernel function is crucial for effective classification. Sample use case that resulted in Challenge 4: an RBF kernel may be unnecessarily complex for linearly separable data. Fixes to Challenge 4. Start with a simpler kernel, e.g. linear, and gradually increase complexity if needed. Use cross-validation to evaluate different kernels and choose the one that performs best on unseen data.